Our next speaker knows biopolyesters inside and out. As vice head of R&D at Ude Inventor Fischer in Berlin and with a PhD from the University of Stuttgart, he's been shaping the future of PBAT, PBS, PLA and Co. for decades and holds multiple patents to prove it. Today, he'll dive into how PBS can be produced continuously, efficiently and with fewer side effects. He'll also show us how existing polyester plants can be cleverly upgraded to get a fast and sustainable start in the biopolymer business. Get ready for smart solutions from someone who's been in the thick of it. Welcome, Dr. Christopher Hess from the well-known company Ude Inventor Fischer GmbH with a speech about the Polybutylene Succinate, new possibilities in the manufacturing of PBS. Welcome, Christopher Hess.
Thank you very much for that very kind introduction. Yes, warm welcome also from my side. Good afternoon. I hope you had a nice lunch, some break, some rest hopefully, and because I think this afternoon will be loaded with quite some PBS. Okay. As you might have seen already, I'm with company Ude Inventor Fischer, which is part of thyssenkrupp, and now I have to figure out how this works. Yes, here we are. Well, I think most of you know thyssenkrupp. thyssenkrupp typically is heavily involved in steel and steel business. So we have different segments within thyssenkrupp. thyssenkrupp is having more or less 40 billions in sales. We have more than 100,000 employees globally. We are located in more than 60 locations, and we have more than 60 countries with more than 1,100 locations globally. And if you see the business areas of thyssenkrupp, well, we are not only doing steel and steel business, yes, we are also doing automotive components, and we also form steel into submarines and these things. But one of the latest things we have done in thyssenkrupp is that we established decarbon technologies. So decarbon technologies is our answer to the future questions which are asked, especially questions regarding a greener and more sustainable future, and also recycling opportunities. And within these decarbon technologies, you can find our latest brand, Nucera, which is dealing with hydrogen generation, conversion of hydrogen into ammonia and methanol. But you also find our polymers in it, because polymers per se are more sustainable, typically we think, than steel. And they also offer the possibilities to produce biopolymers and also offer unique recycling opportunities in the future. So let's look a little bit at my company, Ude Inventor Fischer. We have been founded more than 100 years ago in Berlin. We have two sites, one in Switzerland, one in Berlin, Germany. We have more than 150 employees, more or less evenly shared between our two sites in Switzerland and Berlin. And we are an engineering company. We build plants for the polymer industry, plants for polyesters and polyamide. So one of our latest big success stories was that we have built many plants for the PET industry. PET, we know it all, typically used in bottle applications, but also used for fibers, films, and other engineering plastic applications. A second big product we are producing is plants for manufacture of polyamide, especially polyamide 6, but also polyamide 6,6, SOM 11, and polyamide 12. Applications are typically the same, mostly goes into fibers and engineering plastics. But we also do a lot of biopolymers. We have established our PLA process. We have developed it for more than 20 years. We have sold several plants which are operating and producing PLA from lactic acid or from lactide. We also do, as I explained, we are heavily looking into recycling processes for all of our polymers, especially for PET, but also for PA and PLA. Yes, and we operate pilot plants. We have a fully continuous pilot plant, which is here in Berlin, which can produce polyester, and we also have a fully continuous PLA production plant, which is located in Guben, close to the Polish border. About 20 years ago, we wrote a good story of success. I would say we reinvented the polyester manufacturing process. Up to then, typically, polyester process was depending on a melt phase process, which then finally also went into an SSP, a solid state post-condensation process. This was required to bring the polyester to the ultimately required molecular weight, especially high molecular weights, which are required in the packaging industry. And with this melt-to-resin process, which is depending basically on two reactors, an esterification reactor, which we call the Esprit tower, and a final polycondensation reactor, which we call disc gauge. We could establish that polyesters could be produced with a finally required molecular weight directly in the melt phase. This was a great success, and we established this not only for PET, but this process was also used for PBT, PBAT, and also we think it can be used very well for the production of PBS in the future. So let's look a little bit about how to make PBS. Well, I think we have heard the term PBS quite a lot this morning. I think most of you are very familiar with what PBS is. PBS is basically a thermoplastic polymer, melting point about 115 to 120 degrees. It's crystalline, and it's an aliphatic polyester. It can be produced easily starting out from the monomers, succinic acid, as well as butanediol. You first do an esterification step. Water at temperatures about 200 degrees, atmospheric pressure more or less. You make the monomer, and from this monomer, you then go into polycondensation, and you obtain the PBS. Looks easy, we come to it a little bit later, can be a little bit more complicated than that. But what the good thing about the PBS is, it's a biopolymer. This means it's biologically degradable and also compostable. And on the other hand, it can also be produced partially or even completely from bio-based raw materials. And good news is also it's not a completely new polymer. It's also already available. So in the moment, we see capacities of about 50 to 100,000 tons a year globally, with expansion plans rapidly going on, especially in China. So now this is getting a little bit tricky because I cannot read it completely. What do we see as advantages of PBS? First of all, PBS, I said it's a biopolymer. This means it can be broken down by microorganisms to monomeric units and can be degraded completely. So this makes it suitable for many environmentally friendly applications where biodegradability is a must. On the other hand, we see that the good thermal stability of the PBS. It has a melting point about 115 degrees, which makes it, yes, a good choice for many applications where a good thermal stability is required, but not too high. We also see good mechanical properties. It has good mechanical properties such as tensile strength, elongation, and everything. So this makes it a good choice for polymers where these mechanical possibilities are required. Then we also see good barrier properties. It can be used for many applications where barrier properties are required, especially for packaging applications. And then we see also the good benefit of the processing behavior of the PBS. It can be processed well and easily with existing processing equipment like injection molding, extrusion, blow films, film, and also it can be spun into fibers, what we heard yesterday, which is a good example that you can make from PBS fibers, even artificial leather in these days. So we come a little bit about the possible applications of PBS. Yes, I said that PBS can be used well in packaging applications like containers for food and other consumer goods, trays, even insulation materials, film for packaging and wrapping. Because of its good biodegradability, we see a lot of application possibilities in the agriculture and the marine applications, especially mold films, foil for biodegradable plant pots. Yes, plant pots, a good topic, Mr. Putsch, I think. It can also be used for geotextiles, delayed release coatings for fertilizers, and also for fishing equipment, fishing nets, and other aquatic equipment. It can be used in the automotive sectors, we think, and also in electronics for interior components, trim parts, underhood components, and also for example like covers for smartphones and other electric devices. It can be spun into textiles for clothing and apparel applications, even insulation material, eco-friendly fibers for many applications, even up to hygienic applications and diapers. Then there is a potential, of course, for the biodegradability in medical applications where we can do biodegradable sutures, drug delivery systems, tissue engineering, and these things which are good in medical applications. And finally, yes, of course, this is also a nice application, single-use plastics like disposables, hot drink lids, coffee cups, cutlery, all these things which are nice to have. And PBS can also be modified with inorganic materials like fibers, glass fibers, mineral fillers. We heard this also this morning. So yeah, this can be done very nicely to adjust the properties for the PBS, which is finally required in the final application. Just a quick look at the properties of PBS. For me, PBS is typically a material which is balanced more or less between PP and PE. The properties like elongation, tear strength are more or less exactly where we find other polyolefins like PE and PE. The major difference I see a little bit for PBS is the density. If you buy 1 kilogram of PBS, you get a little, yes, about a quarter less than what you would obtain for PE and PE, which is a little bit of a drawback for sure. So now let's look at how we can produce PBS. And this is always a question of scale. The most easy way to produce PBS is starting with a single batch reactor. You can do this in capacities from 10 kilograms up to 5 tons per batch, which is quite easy. Yeah? You have an esterification reactor and a polycondensation reactor in one reactor. The benefit of such a simple device is the high flexibility. You can use it for making PBS, but you can more or less make every polycondensate in a reactor like this. The next step would be a continuous batch plant where you have an esterification reactor and a polycondensation reactor separated. This typically would be a plant setup for capacities between 10 or 80 tons per day. The next step would be a continuous plant, but always the question is, when is this better? When is this better? Depends a little bit on the capacity. This is an old graph. I just want to give an example. Typically nowadays we would say a semi-continuous batch plant and a continuous batch plant typically would not be, yes, we would separate it at around 100 tons of daily capacity. Beyond it would be more or less a continuous batch plant. Above 100 tons per day, it should be a continuous plant. And yes, of course, finally, a good way to start PBS production could also be you already have a plant, like a polyester plant, a PET plant, or a PBT plant. And then you have already this plant available. It can be modified simply to PBS production. All it typically would require a different final reactor where you can produce the high viscosity required in this new reactor. I will not go through the details of this slide. This is more or less a little bit how we design our reactors, especially for making polyesters and including PBS. The target was always narrow residence time, controlled pressure release, controlled temperature increase, little mechanical components. To sum this up, with our equipment that we have developed over the last 20, 30 years, we think our equipment helps you to do a lot of energy saving compared to standard polyester condensation equipment. And especially with this nice reactor design, we also can have much, much lower building costs compared to standard setups of such plants. In the end, what we want, what our clients want, excellent product quality. And this is what we think we can do also for PBS, because we know this is already working for PET, PBS, PBT, and PBAT. This might look a little bit confusing, but this shall show you how complex sometimes it is to produce a PBS on point. On point means with the properties which are typically required. It's not only the starting materials, the raw materials. Yes, you need some succinic acid we heard and some butanediol, but sometimes also you have to add some additional additives or starting materials like adipic acid. So you should know which raw materials you want to use if you want to make PBS or copolymers. Then you should have a good idea what type of catalyst you want to use. The catalyst is required to produce a monomer in esterification. After you've made the monomer, you should think if you want to functionalize this monomer. Especially here, some melt modifiers could be added. Melt modifiers like tri- or tetrafunctional components like pentraerythrit to modify later on the melt viscosity, which is required especially in injection molding. You don't want to have too high melt viscosity in injection molding, but on the other hand, you want to have a high molecular weight. After you made the pre-polymer by applying some vacuum, you should consider if you want to add some additives. Additives which give you better functionality. Additives which control your stability against UV light, against oxygen, temperature, and water. Typically in the past, then you would have produced a low viscosity polyester from this pre-polymer, and this would have been then gone into an SSP, as I said, a solid state post-condensation process. But this is not a good idea for PBS because of the low melting point of the PBS. What you could do alternatively, you could introduce some chain extenders, highly reactive chemical compounds, which help you to build up the molecular weight quickly. This is no longer required. With our MTR process, you can go directly from the pre-polymer to the high IV viscosity material. Sometimes, before you can ship those chips, you also still have to consider a stripping process, a process where you can remove volatile components which are still contained in the polyester material, or, for example, also oligomers, because for some applications, a too high oligomer content is not a good idea, especially if you want to go into food applications. To sum this up, yes, PBS manufacturing is a little bit more complicated than you might think in the beginning, but with the right partner at hand like us, well, you can design the right process, which is essentially required, especially for your requirements. As I said, PBS is not available, or it's not typically one grade. We differentiate different grades of PBS, for example, for injection molding, film extrusion, or fiber spitting. They are still all PBS, but they are slightly different, especially if you look at the strain at break, or if you look at the tensile strength, or the MFR, which is more or less directly related to the molecular weight. So to sum it up, there is not a single grade of PBS that suits all applications. That's why I said you have to consider already manufacturing of the PBS, what it shall be later on what additional requirements you have regarding additives and melt modifiers. Basically, PBS grades are distinguished by their molecular weight, respectively MFR value. PBS can be produced as neat material for various applications or to fit one selected application. But this neat PBS typically a modification is made before modification is made during or prior to conversion before it's really applied. Now you have made PBS, now you have made PBS product, but now let's look at the end-of-life opportunities of a PBS material. And there again, PBS is, well, I would say like a champion because you have more or less all possible end-of-life scenarios. You can do some mechanical recycling. Yes, we would think this is a good opportunity, especially if you have some post-consumer waste. Post-industrial waste, you can do mechanical recycling, means you re-extrude it. You will see some molecular weight decrease, which can be overcome if you add some chain extenders. On the other hand, PBS is also a very good candidate for chemical recycling because you can do easy hydrolysis, or you can also do methanolysis of the PBS to bring it down to the monomers. If you do hydrolysis, you end up with a succinic acid and the BDO again. If you do methanolysis, you end up with DMS. DMS, a dimethyl succinate, which is also a monomer, which you can again use for manufacturing of PBS. We heard this. PBS is biodegradable. It's possible to do controlled composting in industrial plants, but it's also biodegradable in your home composting facility. And if you look at the composting rate of PBS compared to cellulose or PBSA, it's a little bit less, or it takes a little bit longer time compared to cellulose in composting, but it's still very quickly decomposing after 100, 150 days, which is much, much faster than what we know from PLA, for example. And of course, yeah, you still can burn the PBS if you don't have any better opportunities to get rid of it. Coming back to the monomers you need for manufacturing of PBS. I said typically you would make the PBS from succinic acid and BDO. But there are also alternatives available for succinic acid. I said it's a DMS, a dimethyl succinate, is an alternative, or even the anhydride can be an alternative. All of these chemicals are available in sufficient quantities, more than 100 kilotons a year, which is sufficient to make a lot of PBS in the future. The difference might be, if you start out with succinic acid, we see a little bit of, I would not say disadvantages, but it's a little bit more challenging, like, for example, if you would start from DMS for making PBS. The succinic acid does have quite a high melting point of 185 degrees. This means we must run the esterification under much higher temperatures than we would run a trans-esterification with a DMS. And also the DMS comes typically as a liquid, which makes feeding into a process much, much more simple than if we have to feed a solid substance like the succinic acid. And finally, because of the high acidity of the succinic acid, you are generating much, much more THF in the esterification than what you produce THF in the trans-esterification of DMS. To sum it up, why not look at DMS as a good alternative for manufacturing of PBS compared to succinic acid, which so far is still the standard in manufacturing of PBS. Of course, succinic acid is widely available from several producers globally, and it's also available as bio-based. But some aspects you should consider if you use succinic acid. It comes typically in different size and size distribution values depending on the manufacturer, which makes the esterification process a little bit more tricky. And also you have a higher temperature in the esterification, which in the end generates much, much more THF side product compared if you would start out from DMS. To sum it up, there are different choices for manufacturing of PBS from different raw materials. The good news is you can also have butanediol as well as a succinic acid coming from completely bio-based sources, so you can make 100% bio-based PBS if it's desired. To come back on the DMS, I will not go into details of all this, but to sum this up, nowadays it's possible to produce DMS as well as BDO from one single chemical raw material, which is butane. You first do an oxidation of butane to obtain the malic acid anhydride, and starting from this malic acid anhydride, there are processes available where you just have one plant, one reactor, and you can obtain from this malic acid anhydride as well DMS as BDO. Both essential raw materials for the production of PBS. And if you do a PBS production based on this quite simple and clever process where you have both raw materials available, you can produce PBS at much, much lower cost than what is in the moment available compared to traditional PBS, which is starting off with succinic acid, even PLA or even PBAT. You can produce PBS, in our opinion, as the most simple and most cheap biopolymer in the future if you would use DMS and DMS coming out of this process. So, and this is also more or less my final slide. This is some trials we have done in Berlin in our continuous pilot plant as well as batch plant. So we have made PBS from succinic acid continuously. We have made PBS from DMS in the batch process. And if you compare the values of the PBS we have produced to commercial grades, which are already available, we see that if you produce PBS to our recipe with our plant, we are more or less exactly there where the existing PBS grades are. So this is more or less my remarks. We have produced PBS in many, many trials in the meantime. We have used different raw materials, succinic acid, DMS, bio-based succinic acid. We have optimized the recipe for color. We have played with melt modifiers. We know which extent of melt modifier we want to add. We have looked at end group stabilization and deactivation. We have optimized our BDO recycling system and purification. We know that in PBS production, typically there's a lot of oligomers generated. This can also be recycled. And we also have looked into THF purification, and the THF purification can be adjusted to various requirements. Finally, this is my summary of the presentation. In our opinion, PBS is a very attractive polymer with good mechanical properties. PBS properties can be easily adjusted depending on the final application. PBS can be produced in high quality and efficiently with our Udimenta-Fischer MTR process. Our MTR process is highly flexible to produce different grades of PBS. PBS can be used in a multitude of applications employing standard equipment for conversion. PBS can be produced up to 100% bio-based, which is a good thing. PBS allows for all possible end-of-life options. The most important option, of course, is the biodegradability of PBS. PBS production costs can be lowered by larger plant sizes and by using cost-efficient raw materials. And everything, the dimethyl succinate can be a very attractive material option for manufacturing PBS in the future. So for me, PBS stands not only for polybutylene succinate, but also for possibilities beyond standard. Thank you.
Thank you very much, Christopher Hess. Here is a flower pot for you, biodegradable. Thank you very much for the...
PBS, hopefully.
Yeah.
Of course.
Great.
That's good news.
Thank you for the interesting lecture.
So,
Does anyone have a question from
I'd like
the
to
audience?
open the stage for questions, because that's a very interesting polymer. There might be questions in the back.
Thank you for the presentation. I'm Daniele Falcinelli from Conser SPA, part of Maritech Remote Group. First of all, thank you also to show part of our technology, that is Duetto technology, that can produce both raw DMS and BDO for the production of PBS. So my question is about this new solution to produce the PBS, so the changing from esterification to transesterification. My question is how can improve the market of PBS, and if this solution can really unlock the PBS market. Thank you.
Well, first of all, I think, as I explained in my lecture, if you make PBS from DMS, you can do it more efficiently and more cheap. More efficiently means also you have less side product generation like DHF. And what you have seen also in my slide is that the properties of the PBS produced from DMS or succinic acid more or less are all both the same, and they can compete with existing PBS grades. So then what counts in the end, that's a question of money. Typically, it's always a question of money. And starting out from DMS, this can revolutionize the PBS manufacturing because it offers a much, much cheaper solution. That's more or less what I can conclude from my trials starting out from DMS.
Thank you so much for that. There was a second question in the back. Is it still open, Patrick?
Yeah, so just to get it right, the DMS production is not about fermentation anymore, or is it also a biotechnology process?
In the moment, we don't see a possibility. Yes, you can always make DMS also from bio-based, but what you can make is you make succinic acid bio-based. And then it doesn't make sense to make the DMS out of succinic acid because you can already use the succinic acid in PBS manufacturing. So I don't know any gems that can make DMS directly biologically from bio-based raw materials. I don't know. Maybe in the future, but
Who knows? There's another question in the back.
Sorry. Nice. Thank you for such nice presentation. In terms of producing copolymers, where do you see the most challenging points in terms of as compared to PBS or PLA?
well, the challenging thing is always increase the heat stability and increase the biodegradability. So this is basically what we try to do. Of course, to increase biodegradability, you always have the option to make a copolymer, like if you introduce some adipic acid or other aliphatic acid. And if you want to increase the thermal stability, then of course you are looking in things like PBST or PBAT, where you introduce terephthalic acid units that help to increase the thermal stability.
In terms of production of this copolymer, when we shift from PBS to copolymers, manufacturing process, where the most challenging parts are technology.
So far, we don't see any real showstoppers because our process is very versatile. Yeah, you can produce with more or less the same equipment PBT, PBS, and PBAT. So I would say all copolymers whatever ratio of different acids or diols you are using, that can be handled and can be adjusted with not too much thinking about how to do it.
Thank you for encouraging everyone looking into the future.
Yes.
Thank you for that great lecture on PBS manufacturing, getting more insights also on the chemical and processing level. Warm welcome for you.